This is my 4-legged PCB Robot MKIII, and in this video I'm going to talk about how I designed it and the techniques I used to make it smart, but still cheap enough to use in a swarm. The first thing you need to establish when you're designing a swarm robot is how the robots will communicate. There are three main options: infrared, Bluetooth and Wi-Fi. In my last video I showed the kilobots as an example of the cheapest swarm robots. To get the $14 price tag, they use the same approach, PCB robots. As you can see, they have everything connected onto one PCB and using two vibration motors to move around. These kilobots are using infrared, which is a very cheap communication technique, and this can also be used for proximity, but it also limits their talking range to just 10 centimeters. Another disadvantage of using infrared is that different surfaces can also introduce reflections, which can interfere with the signal. The other two options are Bluetooth and Wi-Fi. I eliminated Wi-Fi because the modules I found were too bulky and expensive for this robot, so it's down to Bluetooth versus infrared. Bluetooth can obviously operate with a much higher speed and also has a longer communication range. Its main disadvantage is that it's more expensive than infrared, and it also has a limited number of nodes, although advertisement packets can still be used to add more robots. Bluetooth is also going to allow me to add a bootloader to the system and have fast over-the-air programming. I can also debug the thing much easier by connecting it to my laptop. I also asked for your advice on Twitter and got some very interesting feedback. Almost half of the people who voted agreed to go with Bluetooth, and others have suggested to use other techniques. One very interesting approach that someone suggested is using ultrasonic sensing to eliminate the problem of light reflections and also increase the communication distance, but ultrasonic sensors are too bulky to fit onto this robot. So considering all the pros and cons, I'm going for Bluetooth. I don't think it's going to be as cheap as $14, but it's going to be a cheapish, smart Bluetooth PCB robot. Just remember that this is a swarm, so the price needs to be calculated on a very large amount of robots. There are thousands of Bluetooth modules that I could choose from, but only one can be the winner. This Bluetooth module is from Cypress Semiconductors. What's cool about it is that it can also be used as the brain of the robot. So in this tiny area it has a chip antenna, and underneath the shield it also has a 32-bit microcontroller. The same microcontroller can handle the Bluetooth stack and receive or transmit messages from the antenna. It's not the cheapest Bluetooth module available, mainly because of the integrated microcontroller, but the price also includes FCC and CE certification. Now I could go for a cheaper option and have the processor soldered directly onto my PCB, but I don't have a network analyzer here to tune my antenna. And I doubt if I can get an smaller than 10mm by 10mm, so I'm going to stick with this module. The most challenging part of every lightweight robot is finding the best battery for it. There needs to be a balance between weight and capacity. But the most important parameter that you need to consider is the nominal discharge current, which is the maximum current the robot can withdraw. Each coil draws around 180 milliamps, so the rating of the battery is going to depend on how much legs can be powered at the same time. To try and increase its operating time, I'm going to limit its movement to one leg at a time, which is the same movement that the Mark II prototype was doing. The weight budget of this robot is around 3 grams, so I need to find a battery in the 1 gram range. This 80 mAh battery fits just in the spec, but unfortunately I don't know its discharge current rating. This has to be to C, ideally higher, so I'm also going to order some more batteries within the spec, so I have more than one option available. Another question that I need to ask is how I'm going to charge this robot. The simplest way to do so is probably by adding a LiPo USB charger. But I'm trying to make a swarm, so every component that I add is going to be multiplied by how many robots I have. So adding a charging IC, some passive components and a connector is going to make the price explode, and will also eat up space and weight from the PCB. It will make more sense to charge all the robots externally. No robot should be wired to get charged. Imagine having to wire up your pets every time they need to go to sleep. It makes no sense. So I'm going to use wireless charging. One option is to use the Lex coil for inductive wireless charging. While it may be very interesting to test that out, I will definitely run out of space on the PCB to implement its circuitry, and the circuitry is also very expensive. So I came up with another idea. Imagine having a piece of copper connected to the outermost part of the spiral coil. I can use these pads to charge the robot and make a tiny little charging station that the robot can sit on. This way, I only have to expose some copper at the edge of the legs, which comes with no extra cost. So we would have something like this. Now let's say two of these are positive and the other two are negative. So like this I could have a simple charging technique. The only problem is that there could be a short over here and over here. Over here and over here. Now I have to be very careful because the electronics itself has to cater for reverse battery protection and short circuit protection. So let's start all over. To simplify the problem a little bit further, only two legs will have these charging pads. These different legs also help me identify the forward position of the robot. Now remember that I only need to repel the coils since attraction will happen naturally from the robot's own weight. So one MOSFET should be enough to drive the backward legs. For the front legs, I had to add an extra MOSFET for each coil. When the leg is powered, both of its MOSFETs are switched on. Now remember that only one leg at a time can be turned on, so the charging pads that are connected to these sides will not cause a short. Because while for example this point is at VBAT, the other charging pad will be floating and disconnected from ground. When the two front legs are not being powered, all of its MOSFETs are off. The charging pads are also connected to an analog channel on the microcontroller's pin and can be read by its internal ADC. If both pins senses the correct voltage, the robot will automatically detect the charging station and enable the charge enable MOSFET, while the other MOSFET will stay off. This has to stay off because otherwise current will be drawn by the coil during charging and make it repel the magnet. To save some space on the PCB, I use the complementary pair transistor for the front legs. This way both size and price are relatively the same to the other individual MOSFET. Since the microcontroller is operating with the same voltage of the coils, I can also get away from using a gate driver. Another problem that I'm seeing in this circuit is the scenario when the battery is completely flat. The supply voltage would be too small to turn on the core of the microcontroller and enable the transistors. So one of the most important tasks is going to be monitoring the battery and make sure that it does not exceed a certain threshold. And when it does, the robot must go into sleep mode. This is the full schematic of the robot. I try to use the least amount of components possible. It would be probably better if I increase the size of the main decoupling capacitor over here and add some protection circuitry, like for example clamping diodes on the ADC pins and the VS diode on the main supply. But then again, this is going to be the first working prototype of the schematics, so I would rather give priority to space and weight just to see that the robot is working, and then add that stuff later on. So until now I have selected a brain for my robots, defined how they are going to talk, move and get charged. That should be enough to make the robot functional, but I'm still missing something very important. What will my robots talk about? Well, the first thing that every robot can determine is how far is he from other robots. This can be done by the Bluetooth RSSI, which is a value in the BM that tells you how strong the signal received is. The closer the robots are, the larger the BM value is. So I can implement a follow the leader kind of algorithm. A robot can also transmit the color of his RGB LED, so nodes that are close by can have the same color. It would be very fun if I could add some more sensors, but as you've probably guessed, I ran out of PCB space. The bottom layer is completely free from components, so that the robot can lay flat on any surface. It just has the copper traces and the ground polygon port. On the top layer, half of the area is left unpoured to give clearance to the antenna. This clearance was given high priority when laying out the board, because any nets that would cross this region can detune the antenna. The remaining area was used to place the other components. Now you have to be very careful when soldering components on flexible PCBs. Bending the PCB might break off the component's pads. So why would I choose to go for this risk? These flexible PCBs are 0.13mm thick. So if there's any chance of getting the robot to a 3g weight, is by using them instead of an FR4 PCB. But to eliminate the risk of components getting broken off my PCB, I place these 4 pads at the edge of the components area. With these 4 pads, I'm going to solder another ultra thin FR4 PCB. which is going to prevent the component's area from bending and also holding the magnets. I calculated the prices of every component I'll be using in this robot. The price of the battery and magnets is just an estimation, so it can be a little bit higher or a little bit lower. This shows that high volumes I can still get this robot to that $14 price tag. Every flexible PCB that I designed so far was manufactured from PCBWay, and this time they were kind enough to sponsor this project. Now it's just a matter of ordering the PCBs and waiting for them to arrive. See you soon.